Welcome to everyone. Thanks also, welcome to the panelists who will be with us today speaking about this very interesting and innovative, I would say as well, aspect of hydropower. This webinar is organized by the International Hydropower Association, supported by ETIP Hydropower, and in strong partnership with Supergrid Institute, who's supporting this event. Today with us, we have an unbelievable, I would say, list of panelists who have gathered huge experience on the topic over the last few years that will share with us some comments, some ideas, their perspective on the topic of hybridization, but they will also go through very interesting case studies. So we will touch upon technical aspect, economic aspect, business-related decision on the process of hybridizing hydropower, existing hydropower plant or new projects. So just quickly to introduce the various speakers that are with us today. First of all, we have Guillaume Amodeo, technical business developer at Supergrid Institute. He has over 20 years of experience in delivering hydropower project. Part of these gathered through working for a leading French EPC company. We also have from Supergrid Institute, Quentin Boucher today. He's electricity market specialist. Quentin has a lot of experience in electricity market economics, and he will guide us through some of the most exciting application that Supergrid is developing in the topic, in the fields of hybridization. Also, Cecilia Correa from International Development Bank. Cecilia is a mechanical engineer. She is responsible for managing the entire portfolio of projects for the Inter-American Development Bank in Uruguay, and she will both contribute providing the bank perspective on this topic, but also we will chat about some interesting studies and work done by the bank on this field. Last but not least, Parvin Nanda, Executive Vice President of Greenco Group. For those who don't know, Greenco is one of our member, very strong partner of IHA. Greenco is developing renewable energy asset in India. They develop and operate for over 20 years, actually. I was reading today the bio of the company again, asset in India. And today we will discuss with them about this integrated renewable energy project, which is a different, if you want, take on hybridizing the operation of hydropower plant. So maybe just quickly, I noticed I jumped the agenda. I will just quickly go through it very quickly. We have first, a very short dialogue with some of our panelists to just set up the scene, just to describe exactly what do we mean with hybridization. Is a very huge topic. It's very debated, but it would be good just to provide a bit of framework. We'll then look at four case studies, actually. And at the end, we have a Q&A with the audience. We really invite all the audience here today to feel free to use that opportunity to drop their message in the chat, to try to interact with the speakers. We'll try to pick up the most relevant questions and make sure that these are responded, and all your questions will be, heard and follow up. Very well. So maybe without further ado, I think it's time to jump a bit more into the content of this webinar. The first question is for you, Guillaume. I really would like just to use this initial opportunity to basically just explain, if you could basically explain what is Supergrid Institute experience in the field of hydropower plants hybridization, and just perhaps simply, what is your definition of hybridization?
Yeah, thanks, Matteo. We all know what a hybrid vehicle is, but when it comes to a hybridization of power plants, and more specifically on hydropower plants, we can all have a different definition, and there is not a single true one. At Supergrid Institute, hybridizing hydropower means combining it with another energy storage system, such as batteries, supercapacitor, and another renewable energy sources, such as photovoltaic. Combining means not only take the opportunity of the grid connection, but also jointly control both storage system or source of production to optimize the services delivered to the grid. Indeed, if we think about brownfield projects, refurbishment, or upgrade of power plant. Most of the time, the grid connection is limited in terms of power capacity. So we do believe that the installation of a battery, for example, a side of the power plant, can be optimized not to be used instead of, but together with. Just a few words about Supergrid Institute. We are an independent innovation company based in Lyon and Grenoble in France. We work on direct current technologies and hydropower flexibility. We work with variable speed. We have different test platforms. But what's most interesting in this webinar is that we have been developing new technologies for energy management systems involving hybridization to improve the flexibility of hydro assets. And we are doing this for run-of-river, reservoir, and pump storage. Moreover, thanks to our participation to Xflex Hydro, we have also developed a strong expertise in energy markets, leading to the setup of a multi-market placement optimization tool. Combined with our experience of hydro technologies, we can thus perform techno-economic analysis of any situation or project. Often, hybridization will be the answer or a part of it.
Thank you, Guillaume. Maybe just to get a bit more of an understanding, so it's really clear that hybridization means many different things today out there, but what are the benefits for operators to consider a hybridization at this stage, at this point in time?
You know, today, from power system point of view, hydropower is seen whether as a base load for run-of-river power plant or peak producer for a hydro with reservoir or energy shifter for pump storage. With hybridization, hydropower now also play a crucial role in short-term flexibility services for the grid. Indeed, there are not many renewable technologies that can restore the imbalance caused by variable renewable energies. Hydro is one of them. We do believe that we should make the most out of it. In terms of benefits, we see four main ones brought by hybridization. The first one is to boost participation to the reserve services. You know, due to physical limitation, hydro units cannot play on fast frequency response services because it requires a power variation in few seconds. So this means no access to this kind of market, and market that are already existing in the UK, in the Nordics, in Italy, some part of the US, and which are becoming more and more in those parts in the world. Second benefit is to increase the operating range. This is to optimize the operation and to maximize the revenues on the automatic reserve market, where hydro can go to, and that is becoming more and more interesting in Europe. I won't explain more because Quentin will talk about this. Third benefit is to reduce the cost of operation and maintenance. You know, whatever the operation, hydro production units are impacted by the integration of variable renewables. More start-stop cycle, frequency signal more perturbed, so more mileage for actuators. Again, hybridization can help, and it is being demonstrated by Vogelgrün, the EDF hybridization demonstrator in Xflex Hydro project. Also, big utilities such as Salto Grande Dam are studying this possibility to fight against faster aging of hydro units. Finally, the last benefit is to maximize or smooth the production of renewable energies. For example, mixing photovoltaic and hydro on the same grid connection point will irremediably impact hydro operation and water management. Hydro peaking, strong variation of water flow and level upstream and downstream, water reserve or ecological flow can also be impacted. A good compromise must be found between solar production, hydro operation, and environmental constraints.
It was a really open question, and I'm glad that you went through a kind of a thorough response, because obviously, depending on the technology you choose, you obtain different results. Depending on the power plant you start from, you want to obtain different solution. But what is really interesting and what I capture from your response is that basically there is a variety of options. There's a variety of reasons why today operators should look at it. It's not only one perspective, the one that matters, but it's adaptable. It's a process, the one of hybrid, it's adaptable to the condition in which the starting point. Tell me what power plant you have, what you need, and we can find a solution through hybridization. That's very good. And very, very briefly, how's the market responding from your perspective at the moment?
We see today a growing interest of many actors of hydro project development. Would it be for greenfield project in islanded grids or big pump storage, but also a hydro producer completing long-term agreement and wondering whether they intend to renew it or they go on energy market. As a technology provider, what is also very important is the demonstration of the solution. In the last few years, we have seen a hybridization project aiming at demonstrating this new way of combining different energy storage system and variable renewable energy sources, and the results so far are promising. We can take the example of Vogelrun in France, Alfalfa in Chile, and other projects to come, such as Valdecañas in Spain or Černiva in Slovakia. As hydropower is facing many challenges, we think that hybridization is a great opportunity to be evaluated in any brownfield or greenfield project, as it provides additional revenues, help in water preservation, and prevent early aging of the equipment. In our opinion, actors from hydropower should embrace this opportunity, and we are here to accompany. Sure, it will be a good topic to discuss together in a few days in Graz.
No. Yeah, I'm looking forward for that. Also, with some of my colleagues will be there, so will be definitely a good opportunity. Maybe just because you mentioned something interesting, which is the age of the power plant, helping age power plant extending lifespan and reducing the operating costs. I mean, one of the great opportunity I see here is that overall we have the global fleet, the hydro global fleet is quite aged. We have a lot of power plants that need modernization, a lot of power plants that need support from the perspective in order to modernize the way they operate, they modernize the service they provide. I mean, someone here definitely who has gathered a lot of experience on this topic is also the Inter-American Development Bank, with all the great job they've been doing in South America, with the support they've been providing to the local fleet in that continent. So maybe very quickly before we jump into the presentation, thank Guillaume for this very good introduction. Just want to capture a very brief comment from Cecilia about what is the bank perspective about hybridization with batteries or hydropower innovation in general. How do you see the role of this innovation? What do you think is going to be the role of this innovation? How the bank work with it?
Thank you very much, Matteo, and good day to everyone. The IDB, the Inter-American Development Bank, is committed to the decarbonization and the energy transition. As a development institution, the bank recognizes the important role the hydropower plays in this process. The IDB has been a key player in the development of hydropower in Latin America. Since 1960, IDB has financed $7.7 billion in investment and $50 million in technical cooperations in the region hydropower sector. As you mentioned, the bank is supporting the modernization of hydropowers. There are right now 2.5 gigawatts being modernized in 4 countries in partnership with organizations like Salto Grande, Ande, and ENE. Undoubtedly, hydropower modernization projects provide an opportunity to introduce innovation and new technologies, and innovation is one of the focus areas of the institutional strategy of the IDB. We are aware that promoting innovation, particularly hybridization in hydropower plants, requires overcoming certain barriers, such as the demonstration and dissemination of new technologies, the development of regulatory frameworks that promotes and value the services that hybrid facilities can provide and enable access to financing. So advancing legal issues related to the use of water surface, and amongst others. So through the bank's operations, we seek to advance in these areas. Okay. Therefore, we are currently executing over $2 million US in non-reimbursable technical cooperation to continue studies on modernization, digitalization, and innovation in hydropower plants in Latin America and the Caribbean. And to cite a few examples, the IDB is currently working in collaboration with the government of Suriname and with support from Japan in the development of a technical, environmental, social, and economic pre-feasibility study for a floating solar project on the Afobaca hydropower dam. This hydro supplies approximately 50% of Suriname's total electricity consumption. This initiative arose from the need to increase the generation capacity as electricity services quality was critical during peak periods in the dry season. This coinciding with the warmer times of the year where there is an increase in air conditioning use and higher solar irradiation. Solar energy in this case will help to mitigate these peaks and optimize water resources management by preserving reserves during critical periods. Floating solar plants could be connected to a transmission line used for the hydropower facility, enabling integrated management of solar and hydro generation. A study conducted by Dorney and Suntrans showed that floating solar PV farm for this dam of 60 megawatt peak and 50 hectares could be installed without violating under load frequency shedding or voltage limits, provided that enough synchronous generation remain online. This floating solar PV plant could contribute to Suriname's NDCs with a renewable solar energy that complement hydropower, particularly during this dry period that I was mentioning before, reducing water discharge from the dam for power generation, integrate the hydropower plant and the floating photovoltaic into a single renewable generation system with the hydro balancing solar fluctuations and serving as an energy storage via the existing grid, allow for additional solar capacity without deforestation by utilizing the Afobaca reservoir, foster local expertise in floating photovoltaic implementation and operation, and ultimately offer economic benefits compared to diesel power generation. Also, the IDB is supporting the government of Mexico to conduct pre-feasibility studies for hybridizing 4 hydropower plants with photovoltaic floating panels. And as I will discuss in more details shortly, we work with Salto Grande and Supergrid on an analysis of hybridization with batteries and hydrogen at the Salto Grande hydropower plant in Uruguay.
Okay, thank you. Thank you, Cecilia. This is interesting. It's always good, I think, to see when financial institution, development banks look at innovation, consider innovation. You actually are, you can be the engine of this process that is really fueling up the development of these new solutions. So I'm really glad that we had the opportunity to discuss this with you briefly. Before joining into the second part of this webinar, where now we are really looking at case studies. So we have gathered for the audience 4 case studies, which I hope will cover a variety of applications, just again to demonstrate how the topic of hybridization can be customized and differentiate. It's not like a single solution that necessarily need to be applied everywhere or for everyone. So maybe for these, I'd like to invite Quentin to take the lead a moment and perhaps speak about these 2 case studies prepared by Supergrid Institute today. We have one for PSP, pump storage of the power in isolated grid, and another one focusing on Peloton units.
Yeah, thank you, Matteo. So I'll be, as you were saying just before, I'll be presenting 2 case studies. I hope you can see my slides now. Okay, so the first one, as you were saying, is about a pumped storage power plant on an islanded grid. And so it is a project that we've been working on for Meridiam, which is an investor and asset manager. And so, as you can see, I'll just put my pointer on. Meridiam has been working for the last 7 years on a pumped storage project in Martinique, French island. Martinique, like many islands, has been relying on fossil fuel electricity for a long time, and it's now integrating, as you can see here, some wind power and solar power, and it's struggling with inertia problems as a small network. So recently, the regulator for the island has been introducing some fast frequency response mechanisms. And it is, as you can see here, a 2-second response mechanism. And so you have to basically, when the frequency drops, you have to increase your power within the next 2 seconds and reach a certain band plus minus 5%. So as you can see here, the response of a Pelton, for example, would not be satisfying because it doesn't enter the required bands within the 2 seconds. And then besides, it overshoots, so it gets out of the band after that. So these fast frequency response mechanisms are quite stringent and can be challenging for hydropower schemes. And it was the case for the pump storage power plants that Meridiam had been working on for the last 7 years. It's a 7 megawatt pump storage scheme, and it was struggling a bit to make the case to the regulator. So this island has no market; it's purely regulated, and this is the context for this study. So we've been working with Meridiam to build a more robust business case for this pump storage scheme, and study different possibilities to provide more, to provide fast frequency response, which was not possible with the existing design. And the goal was to size a system which would be able to provide 2 megawatts of fast frequency response for off-peak hours, because this is the time where the island has the least inertia on the grid. And obviously do this at minimal cost. And so I'll be presenting quickly how we suggested to do that. So to provide these 2 megawatts of fast frequency response mostly in off-peak hours, we suggested to use the existing installations, the existing design, which is made of Pelton turbines with separate pumps, and to run the pumps and the Pelton turbines simultaneously. So this is what we sometimes call a hydraulic short circuit. You might be familiar with this terminology. It's been demonstrated in the X-Flex Hydro project recently in Europe. And so we suggested using this and providing 800 kilowatt of fast frequency response through the hybridization of the Pelton turbines with supercapacitors, because as we'll see a bit later, the Pelton turbines could not provide such a response in 2 seconds. Simultaneously, we suggested a change in the design of the pumps, moving from fixed speed to variable speed, so that enables providing regulation in pump mode, and to obtain 1,200 kilowatts of fast frequency response with the variable speed pumps. We also suggested to repower slightly the pumps, but still staying within catalog sort of pumps sizing. So I was just saying before, doing so, we're able to provide 2 megawatts of fast frequency response, so 800 kilowatts from the Pelton turbines, hybridized Pelton turbines, as you can see here. So you have in black dashed the Pelton response, which obviously is not suitable for fast frequency response. You can see that it's responding much slower, and then it's overshooting besides. And so we compensate with the supercapacitors here in green. And so we make the blue response, which is acceptable for the fast frequency response. And simultaneously, you can see that you have the pump response in yellow, which is 1,200 kilowatts and is as variable speed is acceptable for the 2-second response to fast frequency mechanisms. So to get this together, we have a dedicated EMS, energy management system, which manages the pumps, the Pelton, and the supercapacitors all together at a low level. And so it enables to have a smooth response from the system, from the grid side. And so that's what you have here in blue. That's the power seen by the grid, and it fits the requirements from the grid code within 2 seconds, the response, and no overshoot after that. So in a nutshell, maybe just a word on why we use supercapacitors. As you can see here, we really just boosting the response from the Peltons in the first seconds. So we don't need much power, and this is the great advantage of supercapacitors. We size them very tightly here, and so that enables to lower the costs of the investment. And we need less than 30 seconds of energy from the supercapacitors, and you can get that with supercapacitors. It's very difficult, if not impossible, to get such low energy capacity with batteries. So this is why we use supercapacitors. And besides, supercapacitors respond very quickly, very promptly. And so that's another good point in this case here. I should finally add that Supergood has quite an experience with supercapacitors because we own and operate one of the biggest supercapacitor banks in the world. And so that's the conclusion. You got it. We basically were able to design, redesign slightly the pump storage scheme that Meridiam had been working on with a low investment, but build a project that was more worthy for the system and for the regulator of the island, and also more profitable for Meridiam, the developer. And that was based on both production shift and system services provision or regulation provision. So this was the first use case about boosting the performances of the power plant with hybridization. And I'll move on now to the second use case, which is also about boosting the performances, but mostly about getting more services and in different configurations. And so this is what we call the 100% hybrid Pelton technology. And so this is a study that we did for a theoretical scheme in Finland. So why Finland? Because, as you know, Finland has got a lot of hydropower and it's got well-organized markets there. They've been well-organized for quite a while now. So this study is considering an existing asset made of 2 Pelton units of 5 megawatts. They're quite traditional Pelton units with operating range from 10 to 100%. So with the 2 units, we can go from 0.5 megawatt to 10 megawatts. What's quite important is that we need these Pelton to have the synchronous condenser mode available. That will be quite important for the technology, for the 100% Pelton technology. And lastly, it could be done with any kind of Pelton units, but it's even more interesting, and that's what we've taken here, if the Pelton have got quite a bit of storage. And so here we've got more than 1 week's worth of water storage. So the technology that we'll be studying, the Pelton 100%, here applied here is just a small investment for a 600 kilowatt lithium-ion battery. And this enables to have regulation not only from 0.5 megawatt to 10 megawatts, but from 0 megawatt to 10 megawatts. So from the synchronous condenser mode to 10 megawatts. And so that's basically like having behaving like a big battery of 10 megawatts. And so this is done through the coordinated control of the Pelton and the lithium-ion battery. I'll be going through a couple of benefits or cases that this technology could be beneficial. The first one, and it's the least one, is when the prices are high on the day-ahead. And we did a study using real prices from 2022 in Finland. You have on the top the existing assets, and on the bottom the hybrid Pelton 100%. And you have the case of the 8th of March of 2022. And so when you have high prices on the day ahead, you'll be bidding with your Peltons here, or you'll be providing energy to this level. If you don't have markets, could work as well. And with the previous technology, with the business as usual, you can provide reserve up to 0.5 megawatts and 10 megawatts on the top. Whereas with the Pelton 100%, you can go down to 0 megawatt. And so that's what you can see here from 6 a.m. to 9 a.m. We provide the same amount of energy in dark blue than the existing assets, but in green we provide much more reserve, automatic reserve. So that's the first benefit that you can get here in high prices day ahead or peak hours. You can provide more reserve, providing the same amount of energy on the day ahead. Now, when the prices are low on day ahead, that's even more interesting, and that's what you can see from 3 p.m. to 6 p.m. When the prices are too low on the day ahead, the existing asset does not provide any energy. As it's not spinning, it cannot provide any automatic regulation. Now, with our technology, 0-100%, Pelton 0-100%, you can be in synchronous condenser mode, so use no water or very little, and provide up to 10 megawatts of upward secondary response. And that's what you can see here. We get from synchronous condenser mode, no use of water, no placement on the day ahead, but we provide in green 10 megawatts of automatic response upwards. And another case when the prices are low, but the prices of the reserve are sufficiently high, you might be tempted, and that's what we do here, to use some water to provide energy, to be spinning, and provide the regulation to get the revenues from the regulation. That's what you can see on the existing assets from 10 a.m. to 2 p.m. But with our technology now, we don't need to be using water to be spinning. We're just going from synchronous condenser mode, and then we provide the regulation up to 10 megawatts. So just to summarize, this 0-100% Pelton technology enables us to boost the revenues on the reserve markets by providing more reserve at any set point. But we also preserve water because now we can provide automatic reserve without providing energy on the day ahead. So even from synchronous condenser mode. So that's what you could see in the early afternoon of the 3rd of the 8th of March. And finally, the return on investment of this technology here in this case was less than 5 years, but it has to be studied case by case, but it shows that it could be very interesting.
Thank you, Quentin. This is the end of
yes,
slide.
yes.
Yeah. Thank you very much. I think this was very interesting. I think first of all, I'd like to underline how there's a pattern already on. We are looking at a Pelton unit. I had a Pelton unit, then we've been speaking about the pump storage hydropower. We have heard in the past also, you mentioned it, flex hydro, run-over-river hybridization. So this really already demonstrates how actually it doesn't matter what type of asset you have. There is always a way potentially to improve the flexibility, optimize the flexibility provision from that asset through hybridization. Very quickly, just a comment before we jump to the next presentation is: have you tested? Have you tested any of these solutions, these technologies at the moment?
Yeah, thank you, Matteo. We've got various projects at different stages of development. None of them is yet in service, but the first project that I presented, the Saint-Pierre, the pump storage scheme in Martinique with Meridiam, is now got over the line with the regulator with these new services that we provide with hybridization. So it should be developed in the next few years. We've got also some studies with Artelia in Cabo Verde, and that's hybridization and smoothing also solar production. But we've been demonstrating these technologies on our transient platform, Hydro Feel. So that's a real-time platform as well. And finally, for the Pelton 0-100%, we're looking for a demonstrator, a physical demonstrator to demonstrate or to install our technology. Yeah.
Good to hear. So if there is anyone out there in the audience, perhaps as well, or among the panelists,
exactly.
That's a good opportunity to know that you have this chance to cooperate with Supergrid in the development of this solution. Also, because I saw that in the Q&A. By the way, thank you all the audience for keep dropping questions in the Q&A, in the Q&A chat. Sorry. I saw a lot of questions were specifically focused on the Pelton on the Peloton application. So I'm sure I'm seeing that there is a lot of interest on that. I'd like to move forward now and take you, Quentin, for this presentation. Cecilia, would you mind maybe now taking the stage to present a little bit what the bank has been doing with the Salto Grande project?
Of course. Thank you, Mateo. I would like to share with you the analysis of storage integration in Salto Grande hydroelectric power plant that was developed to analyze the optimization of the plant's operation and reduce equipment wear, in which the bank supported the institution through technical cooperation and Supergrid Institute provide technical support. The next slide, please. Salto Grande binational hydroelectric power plant is jointly owned by Argentina and Uruguay and has been in operation for 45 years. It has 14 Kaplan turbines and a total power of 1,890 megawatt. It is now undergoing a modernization through a strategic investment plan, and Salto Grande is leveraging modernization process as an opportunity for innovation by analyzing the inclusion of storage technologies to reduce the wear on guide vanes and runner angle actuators. Please, next slide. This study is driven by the increased demand for system flexibility to the growth of renewable and intermittent resources like wind and solar. Hydroelectric power plants are becoming more crucial for their energy storage capability and flexibility, but they also face increased operational demands and equipment wear. Next one, please. The Salto Grande hydroelectric complex is one of the main frequency regulators in the interconnected Argentina and Uruguay systems, which has a high share of variable renewable energy. Salto Grande's Kaplan turbines regulate frequency by adjusting their power production through a combined action, the double regulation of the guide vanes and the runner blades angle. And this study explored the use of chemical batteries and hydrogen production with electrolyzers to reduce the movement of the actuators due to primary frequency regulation, which is their main use, as you can see in the figure below in the right. The next one, please. The following storage technologies were evaluated for primary frequency regulation. Electrochemical batteries, which are characterized by their power and energy storage capacity and can respond to both high and low demands. The main challenge in this system is to ensure that the battery state of charge remains within an acceptable range to act when needed to reduce the movement of hydraulic actuators. Then the other technology was electrolyzers for hydrogen generations, which are characterized by their power. This technology can only respond by consuming energy. The hydraulic system must operate above the control band to allow the electrolyzer to consume the necessary energy for frequency regulation. The operating point of the electrolyzer should be shifted to the middle of its operating range. Just if it's from 10 to 100%, it should be set at 55% of its nominal power. The figure below on the right shows how the hydraulic system generally remains at constant power, that's the orange line, while the electrolyzer handles most of the frequency regulation, that's the blue line you can see. Only when frequency deviations are too large to be managed by the electrolyzer alone, the hydraulic system completes the plant's response. With electrolyzers, what you have at the end is that you will have less electricity injected to the grid as it will be used for hydrogen production. Next one, please. For the batteries, 942 power energy sizing pairs were considered and 156 pairs were selected in the area of interest between 17 megawatts and 6 megawatt hours and 346 megawatt and 321 megawatt hours. The simulation provided access to the set of economically optimal power energy pairs to reduce actuator movements, as shown in the graph below. It can be observed that the selected technologies reduce actuator movements due to primary frequency regulations by between 90 and 99%. And for a given reduction in movement, there is indeed an economically optimal solution. The next slide, please. Now, if we go to the hydrogen electrolyzer, several simulations were conducted with different size of PEM electrolyzers. Within the range of electrolyzer studies, the reduction in actuator movement due to primary frequency regulation is between 60 and 99.5%. A preliminary analysis was also conducted on the water and electricity consumption for hydrogen production. For example, a system that allows a 93% reduction in actuator movement related to primary regulation, that it will be of 60 megawatts and around 100 million US dollars, results in a loss of electricity production representing approximately 4% of Salto Grande output, which is actually converted into hydrogen, of course. And for both studies, batteries and electrolyzers, a preliminary sizing analysis of the system components was conducted. And finally, to conclude, the analysis shows that both alternative studies are technically feasible for significantly reducing actuator movements. However, it is necessary to evaluate the economic benefits associated with the reduction in actuator movement to fully assess the feasibility. This was actually one of the questions on the chat. However, the technical team at Salto Grande believes that the benefits are considerable, but have not yet been quantified. That's it.
Oh, sorry, I was muted. Thank you, Cecilia. This is very interesting. I think what I really like of this case study is that it showcases a methodology. You know, I have a feeling that the technology is there. We are blending technologies that we know well, where most of the work and most of the game is really about what is the best way to integrate them, how to control the integration between two technologies that were originally not designed to work at the same time in a unison. And there is where innovation is at the moment doing most of the work, and I think the work done by the bank in that direction was important. Maybe can I just ask you, what is the status of this very interesting project and study?
Yeah, of course. Well, Salto Grande is now analyzing both alternatives. Regarding hydrogen, Salto Grande will work with IDV to initiate the selection process for a comprehensive evaluation of the feasibility of implementing a hydrogen production system at the hydroelectric complex. This evaluation will consider technical, legal, commercial, and environmental aspects to ensure an effective contribution to energy transition and operational sustainability of the complex. Excellent. And regarding the batteries, the project has been presented to the Global Energy Alliance for People and Planet, seeking support for the design from NREL, and we will see what happened with that. But what it is important to highlight is the difficulty in estimating the monetary benefit of reducing actuator movement. While it is known that there is a reduction in demands and wear risk, translating this reduction into monetary terms is challenging. Some studies suggest, for example, a 5% performance increase, but it is difficult to apply these findings to a specific case of the plant. In this case, the decision to proceed is based on technical conviction. However, an estimate of the improvement will likely be necessary when moving forward with the final investments, of course.
Thank you. That's a very important point, the one that you made about how difficult can it be to really quantify cost saving associated with some of this technology. But I think that is really where all these case studies, where all these initial application, this research will provide clarity. I'm sure this is a problem. I'm convinced at least that this is a problem that we have now because we have a gap in our knowledge. But in 5 to 10 years, when we have definitely accumulated all that type of experience, all this will become something like clear and transparent and I'm sure undisputed. But hopefully that at least is the horizon. Thank you, Cecilia, for this question. Now we have seen a case, as I said before. I like this process where we've seen a case of a Pelton high head unit, then a pump storage, and now we'll be speaking about a Kaplan, so a run-of-river plant with a very low head. So now all these been hybridized, but now we're going to completely change the game. Greenko is trying to do something very different from this perspective. It's a hybridization, but on a huge scale, basically, the one that Greenko is proposing. So maybe Nanda, first of all, thank you again for joining us today. I would like to give you the stage now, perhaps, to discuss a bit about the project that the Greenko is developing.
Yeah, thank you, Matthew. This project which we are going to talk about is a integrated renewable energy storage project. Now, this is first of its kind and maybe the largest project in the world as of now. Next, please. Next. Yeah, I'll just give a brief that what we are trying to do in Greenko is we started with a project development company, and then we are now shifting towards the creating storage services. So cloud storage, and we are in plan to get around 100 gigawatt hours of storage on board by 2029. And then we'll be using this low-cost storage pool for creating the decarbonization solution provider that's turning to molecules. So we plan to have around 20 to 25% market share by 2030 in the storage, and around 40% share in the green molecules later on. Next, please. This is brief that we have around 7.3 gigawatt of the commissioned potential as of now, which is a mix of wind, solar, and hydro. You can see wind is around 3.2, solar is around, hydro is around 1.9. So that's a mix we have for the for all three. Next, please. This is what we are trying to do on the storages. You see, we have 8 projects on the list which we are doing. These projects are planned to have almost 130 gigawatt hours of storage. And then last bottom two projects which you see in the green are the integrated projects. Both of these projects are around 5.3 gigawatt projects, which include solar, wind, and hydro all put together. Next, please. Now coming to the one of the projects which is under execution and is nearing commissioning. We have already commissioned 2 machines in the pump mode, and water filling is going on, and we'll plan to commission first machine commercially by end of this year. This project is in total of 5.23 gigawatt project, wherein solar component will be around 3 gigawatt, 550 megawatt will be wind, and the storage component is around 1.68 gigawatt. So this project in all puts 5.23 gigawatt of the hybrid sources together to give a stable supply of around 1700 megawatt at all points of time. Next, please. This is the structure of the project. This is behind the meter integration of all the projects. Solar, wind, both are integrated to a central pooling station along with the pump storage projects. Whereas one side movement is from wind and solar projects, and the pump storage will have both side movement. It will absorb power and it will release power also. And the stable power, all power balancing will be done in our central pooling station, and balanced powers will be supplied to grid. The beauty of this project is that we have 5.23 gigawatt of the project, but the grid connection requirement is only for 1700 megawatt. Next, please. Next slide. Yeah, this is the structure of the central pooling station. We will be having we call it a Greenko load dispatch center, because it's a multiple combination where we have all forecasting, planning, balancing, everything will happen at this stage only, and the final regulated power will flow to the grid. This is an architecture shown for that. Next slide, please. These are the products which come out of this project. This project is capable of supplying all basic products required for the output which we are looking from the hybridization. This project is capable to supply round-the-clock power. It can supply BESS plus peak load servicing. It can supply storage per ancillary services. It can supply on-demand schedulable energy services. So whatever the market needs, this project being behind the meter integration is capable of delivering all products. So that's the beauty of this project. And all these 3 sources are co-located in this particular place. Next, please. Thank you. This is brief. I just wanted to give about this project, that what is this project, and we are now commissioning this project. 2 machines are commissioned already in the pumping mode, and hopefully the full commissioning of first machine will happen by commercial generation will start by December. Thank you.
Thank you, Nanda. This was very interesting, and I think a very good contrast with what we've seen previously as well in terms of approach. Can I just maybe just a little word. We're speaking here about a huge asset, no? More than 5 gigawatt in total. Having this integration between a power storage plant that provide a certain advantages in absorbing and improving the production profile of two large variable renewable energy plants as wind and solar. Does this somehow help in the financing of these sides of this asset of an asset of this size?
Matthew, if I am to talk about in Indian context, since this project is located in India only, the situation has changed quite a lot in last 4.5 years. When we conceptualized this project at that point of time, this hybrid conceptualization co-located was very well taken by the financing agencies at that point of time, because it was a new concept and it was covering many issues which are there with the non-co-located project, like losses in the transmission lines, deviation settlement mechanisms, etc. But now the policy framework in India has changed drastically in last 4 years. Now there's no specific advantage for creating these projects for a financer. So co-located project is now as on date is at par with a non-co-located project from the financing perspective.
Okay, I see. Thank you, Nanda. That's good. I don't know if anyone else want to add something. And I invite actually, well, just overall, we have concluded with the presentation. Thank you, Nanda, and the case study. So I think that it's good because we have 8-9 minutes now before the end of the webinar to respond to some questions from the audience. And I've seen that we have a very busy chat. I invite speakers, panelists to just take over some of this question, either in the chat or maybe as a point of discussion or conversation for the webinar. But there is just one that maybe was good for you, Nanda, since you've just been now closing and speaking about the integrated plant. What are the key and technical challenges of combining hydropower with other renewables like solar and wind? How can these be addressed to maximize sustainability as well, they're speaking?
See, this was a really big challenge for us to do that at that point of time. And we did a lot of work on that point of time. We thought about putting up variable speed machines because we are integrating behind the meter. But eventually, we came out with a solution which was lower cost and more optimal. As Golima also said about the hydraulic short circuit, we are using machines of two sizes in this case. We are using 240 and 120 megawatt size of machines. These two different sizes of machines give us a lot of flexibility in absorbing the power. So the infirmity of the solar and wind, which is there, we are able to absorb from 0 to 100% with those, with just a minimal black spots at the top and corner, and that's it. So that is how we are able to absorb most of the power, cover up all you can say shortcomings of the renewable power to make it a stable and firm power. So that's how we have conceptualized this project to use this power.
Okay, thank you. I don't know if anyone else want to add something on this topic. Otherwise, I have a question picked from the chat. A curiosity from someone was asking if there was any consequences for the Pelton unit to be run in synchronous condenser. Maybe either Quentin or Guillaume, I don't know if one of you wants to pick on this one.
Yeah, thanks, Matteo. Well, the Peltons are usually the Pelton which have the synchronous condenser mode available. They're usually used in this mode even when they don't produce to provide voltage regulation. So yes, there is some impact on these units. However, these units are in air at this moment, so it's much less than if they were full of water. And I mean, it wouldn't be quite different from what they would be doing without the technology, because most of the time, I mean, some of the time at least, they would be using them in synchronous condenser mode to provide voltage regulation.
Okay. Okay.
No, enabling to provide regulation while you're already providing voltage regulation. frequency regulation. Yeah.
Okay, yeah, it's a combination of the two services, basically.
Yeah.
Yeah, perfect. Maybe I have a question for Quentin, and again, you, or maybe beyond, or also Cecilia. I'd be happy perhaps if you have something to add in that. They're thanking for the hybridization examples, but I also like to know more about how did you can you overcome regulatory obstacles to changing the interconnection characteristic of the FOM asset with grid operators, or front of the meter asset with grid operators? I don't know if
I can, I mean, if you want to jump in, Cecilia, please do. But I mean, that would require discussions depending on where you're located, which country you're located. This is a discussion that you need to have, or we need to have, and we can help with that directly with your regulator or your TSO, your transmission system operator. There's no one fit for all answer here, unfortunately. I'm sorry. It will largely depend on the willingness of your regulator, on their liking or not the new technologies, the hybridization, and so unless there has been some previous cases in your country, which then will lead the way for the next ones. But if there has never been any hybridization in your country, then it will probably need to have an extra step and discuss that with the regulator and the TSO. But at Supergrid Institute, we're here we do studies to help support this process and demonstrate to the regulator and the TSOs that seen from the grid, everything is seamless. So they won't be seeing anything that they wouldn't like to see.
Maybe Cecilia, you want to add something?
Yes, just thank you, Quentin, for the response. Just to add, yeah, it's definitely, these are new technologies or new uses for the technology, so regulation has to be adapted. So it requires close collaboration with regulators and the technical part of the operators. From the IDV, what we are trying to do is to support the different operators and the governments to undergo these barriers through this technical cooperation that I mentioned before, that not only analyze the technical aspect, but also the regulatory and legal aspects, not just those regulations, but there are legal aspects regarding I mentioned before, for instance, the use of some operator can use the water for generation, but for instance, not use the water for locating the solar PV panels in the top of the lake, so of the dam. So changes need to be done, and it needs a joint work between all the actors.
Yeah, that's a very, very valid point, very important point, actually, Cecilia. Thank you for this additional contribution. Just apologies if I sound a bit rushed, but because we have so many questions in the Q&A, I'd like to make sure that more or less at least a good portion of those are somehow considered in this conversation. There was maybe another question that where Supergrid could provide a contribution is when we speak about Pelton 0 to 100% case study, the ROE less than 5 years, they say, is very interesting, but the pricing in March 2022 were quite high. Have you run a sensitivity analysis on different prices? Do you still see it interesting, perhaps in energy prices from 2019 or the existing one, the one at the moment? What's your take on that?
Yeah, it's a very interesting question, and I guess I wish I had a crystal ball to see the future, but I don't. Agreed, the prices in Finland, in particular, in 2022, were not the lowest that we've ever seen. So it would definitely change the profitability. Now, I would be tempted to say that we would have to run the numbers case by case, and that's a bit what I was saying in the presentation. I know it might be a bit of a frustrating answer, but it is. Now, for example, in this case in Finland, we only considered secondary regulation and primary regulation. But in Finland, for example, they also have fast frequency response. We did not consider these. There were a couple of other, I mean, we basically simplified a lot our technology, and there were a couple of other details, not so details, but that we didn't take into account, so that would also add up. So there are plenty of other ways to add. You know, I've presented the small, I mean, the hybrid 0-100% Pelton that we can do, but there is also other things that you can do with the batteries, and so there's plenty of ways to add up. But yeah, it would have to be looked at individually.
It's all about revenue stackability, basically, as we already discussed many times in the past. It's difficult, especially when you run a study of this type, to consider all the various markets at the same time, and you have to make some choice. But what is interesting is that often you might study a solution to provide, once you increase your flexibility of a power plant, then there might be multiple markets where you can trade it in the future, and multiple opportunities to capitalize on it. And it's difficult sometimes to forecast them necessarily in advance, because the energy sector is going through this huge transformation, and we are changing the role of hydropower plants. We are changing the way they are operated. And here we are today trying to, with innovation, trying to make sure that their flexibility is maximized, their contribution to the energy transition is the best possible one. Maybe just because we've been speaking before we close, because we are now 1 minute long, just very, very close comment, because Nanda, we have been speaking a lot about regulation of the grid with all the other solutions. The integrated project that you are developing, is this also involved, I imagine, with the provision of grid control and balancing services, correct?
Yeah, Mitty, you're right. This project also has the built-in facility to control the grid control or ancillary services. We have a twofold requirement. We have to balance within the our system, and we have a provision to support the grid as well. We can do it in both cases. We can internally support, and since we are supplying balanced power outside, so the role within our system is also very important to us, and we have that capability of frequency regulation within our system as well. So that role will be played by this project.
Fantastic. Thank you, Nanda, for this last brief comment on your project. I think we have said enough today. We definitely even went a few minutes longer. I want just to take a last opportunity to thank all the panelists participating to this webinar. It's good for the industry in general. So let me thank you from IHA perspective for having helped us in organizing this event, which I'm sure has helped some of the players understanding better what hybridization can be and how can it look like, providing a range and a variety of examples. But I'm sure we have definitely somehow provided an input to the sector, demonstrating how hydro is not been done. Hydro is not finished. Hydro is at the core of this transition, and hydro will be there playing the role that they played in the past, but also providing all the new type of services that will be needed in the future in this dramatically and radically changing energy landscape. So one more time, thank you, everyone. Thank you for also the audience for the very interesting questions. Some of them were very, very pointy. And thank you for the IHA team for the huge support in organizing all these. I think this can be the end of this very interesting webinar. Thank you very much.
Thank you, Matthew. Thank you, everybody.
Thank you, everyone.
Bye.
Bye-bye.
Bye.